Welcome to Academic Math. In this video, I'll solve question number 4 of exercise 2 of the book Higher Algebra by Mapa. In this question, a relation beta is defined on Z by x is related to y by the relation beta if and only if 5 divides x square minus y square, then so that beta is an equivalence relation and hence so that there are 3 disjoint equivalence classes. Now, first we will try to show that beta is an equivalence relation. As we know that five divides 0, which implies 5 divides x square minus x square for all x belongs to Z. For all x belongs to Z, and this implies that x is related to x by the relation beta for all x belongs to Z. As x is an arbitrary element, therefore we can say that rho is reflexive. Now, to show rho is symmetric, let x is related to y for x y belongs to Z. Then 5 divides x square minus y square. As 5 divides x square minus y square, therefore x square minus y square will be 5 into k1 for some k1 belongs to Z. K1 belongs to Z. There exists such k1 as we have already taken that x is related to y. Now we will show that y is also related to x, that is 5 divides y square minus x square, and which implies that y square minus x square equals 5 into minus k1, which implies that 5 divides y square minus x square. As k1 belongs to Z, implies minus k1 is also belongs to Z, and therefore y is related to x also by the relation beta. Hence x is related to y implies that y is related to x, and therefore the relation rho is symmetric. To show rho is transitive, let x is related to y and y is related to z. For x, y, z belongs to z, bold z, that is sets of all integers. Then we have 5 divides x square minus y square and 5 divides y square minus z square by the definition of the relation given. So therefore we have x square minus y square equals 5 k1 for some k1 belongs to z, and y square minus z square equals 5 into k2 for k2 belongs to z, and hence and therefore x square minus y square plus y square minus z square equals 5k1 plus 5k2, as for k1 k2 belongs to z. Okay, now this implies that x square minus z square will be equals to this implies that x square minus y square will be equal to 5 into k1 plus k2, which implies x square minus z square equals 5 into k3, as k1 k2 belongs to z. This implies k1 plus k2 is also belongs to z. Let k3 equals k1 plus k2. This implies that x square minus z square will be equal to 5 into k3. This implies that x is related to z by the relation beta. Hence x is related to y, y is related to z. Both implies that x is related to z, and therefore the relation beta is transitive. Hence beta is an equivalence relation. Now our target is, we have to show that beta, the relation beta divides z into 3 distinct equivalence classes. The second part, that is, we have to find out the classes, all the classes formed by the relation beta. Since we know that every equivalence relation forms a partitions on the set by the equivalence classes. Now any integer upon division by 5 will leave remainder leave remainder 0, 1, 2, 3 and 4. Therefore there are 5 equivalence classes, may not all distinct or may be all distinct. They may all distinct or may not be all distinct. We will check that they are all distinct or not. They will not be distinct because there are 5, and we have to show that there are 3 distinct equivalence classes, and therefore there are only exist 2 equivalence classes who are same. That is, one class belong to the one element of one class belong to the other class. Now, by the definition of the class of 0 equals the element x belongs to z such that x is related to 0. That is, class of 0 means the element which belongs to z such that 5 divides x square minus 0 square. Similarly, we can write here that class of 1 will be equals to x belongs to z such that 5 divides x square minus 1 square. Similarly, class of 2 will be equals x belongs to z such that 5 divides x square minus 2 square. Class of 3 is x belongs to z such that 5 divides x square minus 3 square, and class of 4 is x belongs to z such that 5 divides square minus 4 square. Now our claim is that class of 2 and class of 3 are same, that is, they are not distinct, and class of 1 and class of 4 are same. To show this, we will show that 2 belongs to the class of 3 and 1 belongs to the class of 4. Our claim is that class of 2 is equals class of 3. This is our claim. This and class of 1 is equals class of 4. Now we will show that these two classes are same, as 5 divides 2 square minus 3 square, as 2 square minus 3 square equals, since 2 square minus 3 square equals 4 minus 9, and which equals minus 5, and 5 divides minus 5, that is 5 divides this, so we can say that, which implies that 2 belongs to class of 3, and similarly, and two belongs to class of 2. So 2 is the common element between the two class of 3 and class of 2. So by the property of equivalence classes, we have two equivalence classes. They are mutually either disjoint or have the same elements, either equal or mutually disjoint. Two equivalence class will be either same, or that is either equal or mutually disjoint, and then therefore by the property of equivalence classes, therefore by the property of equivalence classes, we have class of 2 equals class of 3, and similarly we can show that since 1 square minus 4 square equals 1 minus 16, which equals minus 15, as 5 divides minus 15, this implies 5 divides 1 square minus 4 square, and this implies that 1 belongs to class of 4, and 1 always belongs to the class of 1, and therefore 1 is the common element. If similarly by the property of equivalence classes, if they have a common element, then they are equal, and if they do not have any common element, then they are mutually disjoint. And therefore by the property of equivalence classes, class of 1 equals class of 4. Hence finally we have three mutually disjoint equivalence classes of Z by the relation beta, and they are class of 0, class of 1 equals class of 4, and class of 2 equals and class of 2 equals class of 3. These three are the disjoint equivalence classes. Thank you. In the next video I will solve the next two questions, that is question number 5 and 6.